Dear students, in previous class we were discussing about the prime numbers and some of its properties. Now let us discuss about another important theorem. If a prime P, let P be a prime, if P divides the products A and B, if P divides AB, then either this P divides A or P divides B. P is a prime. If P divides AB, then P divides A or P divides B. Okay. That means, how to prove this one? So its proof is, let P divides A. If P, and P does not divide C. P divides AB and P does not divide C. P does not divide A means GCD of P and A are 1, means P and A are relatively prime. So P divides AB and P does not divide A means P and A are relatively prime, means we have P divides AB and A and B are relatively prime. Okay, this statement modified into this way: P divides AB and A and B are relatively prime. Then we know that by Euclid's lemma, Euclid says that if A divides BC and A and B are relatively prime, then A divides C. So this is Euclid's lemma. If A divides BC, A and B are relatively prime, then A divides C. So by Euclid's lemma, if P divides AB and A and B are relatively prime, this should imply P divides B. Okay. Similarly, if P divides AB and P does not divide B, P does not divide B means GCD of P and B is 1, means P and B are relatively prime. So that is P divides AB and P and B are relatively prime, then by Euclid's lemma P divides A. By Euclid's lemma. Okay, by Euclid's lemma. So that means this then combines P divides AB implies either P divides A or P divides B. So this is the proof. Okay, P doesn't divide A means P and A are relatively prime. Then by using Euclid's lemma we have P divides B. And similarly the next case. So finally P divides AB means either P divides A or P divides B. So suppose P divides A1, A2, etc. A. You can generalize this result. If P divides A1, A2, etc. A, then P divides either A1 or A2 or A3, etc. or AN. How to prove this one? Means P divides A1, A2, etc. AN means P divides AI. P divides AI for some I. So this is the generalization of this result. If P divides A1, A2, etc. AN, then P divides AI for some I. So how to prove this one? P divides A1, A2, etc. AN means here P divides AI on, according to this argument, P divides AB, then either P divides A or P divides B. Here P divides A1, A2, etc. AN means P divides A1 or P divides the product A2, etc. AN. That means P divides A1, or here again it is P divides A2 or P divides A3, etc. AN. Then proceed like this. Then finally we have P divides AI for some I. Okay, so this is the generalization of the first result. Agreed. Okay. Now let us consider an important result, which is a well-known theorem. The theorem is known as the fundamental theorem of arithmetic. The well-known theorem is fundamental theorem of arithmetic. What is the fundamental theorem of arithmetic? The fundamental theorem states that every integer n greater than 1 can be expressed as the product of prime factors in one and only one way, apart from the order of the factors. So this is the fundamental theorem of arithmetic. for any integer greater than 1 can be expressed as the product of prime factors in a unique way. The uniqueness is preserved in a unique way apart from the orders of the factors. How can I prove this one? How can we prove? So, the proof is done by induction hypothesis. When n equals to n greater than 1, when n equals to 2 is a prime, so the result is finished. So when n equals to, the result is true, it is true. Result is true. Now suppose the result is true for every integer greater than 2 and less than n, or every integer greater than means the result is, next we assume that the result is true for every n greater than 1 and less than n. The result is true for every integer greater than 1 and less than n. Okay. So now for induction, it is enough to show that the result is true for n. That's our requirement. Okay. Now when n is prime, nothing to show. When n is prime, nothing to show. Why? Our requirement is n greater than 1 can be expressed as the product of primes. So when n itself is a prime, nothing to show. When n is not a prime, suppose then n is a composite number. N is a composite number. If possible, this n can be expressed as the product of primes p1 etc. ps. If it is possible, there exists another expression, it is q1 etc. qt. Means this composite number n can be expressed as the product of primes here. Now the uniqueness is also our requirement. So in order to prove the uniqueness, we have to show that this s equals t. Okay, s equals t and p equals q for some q. Agreed. We have n equals p1 etc. ps equals q1 etc. qt. Okay, this one. That means this p1 that divides this q1 etc. qt. Why? Listen here. Here p1 into etc. ps equals q1 into etc. qt. That means q1 into p1 into p2. p1 into p2 into etc. ps equals q1 etc. qt. That means this q1 into qt equals p1 into p2 into etc. into ps. They are all integers. So the product p2 etc. to ps is also an integer. Thus q1 etc. qt is nothing but a multiple of this one, multiple of this p1. Therefore q1 etc. qt must divide, p1 must divide q1 etc. qt. Agreed. Why? Because you can express this q1 etc. qt as the product of this p1, as a multiple of this p1. Not product, as the multiple of this p1. Agreed. So p1 into p2 into etc. ps equals q1 into etc. into qt. Means this q1 into etc. into qt can be expressed as a multiple of p1. That means p1 must divide q1 etc. qt. p1 must divide q1 etc. qt means p1 must divide this qi for some I. p1 must divide this qi for some I. That's immediate. Okay. In particular, this p1 divides q1. What happens here? p1 divides q1. p1 divides q1. This means p1 equals q1. Why? Because pi and qi all are primes. So one prime divides another prime means that happens only when they are same. So p1 divides q1. Since p1 and q1 are primes, clearly it is p1 equals q1. Okay. Therefore, this can be rewrite as this n equals p1 into p2 into etc. into ps equals this q1. What is q1? That is p1 there. So it is p1 into q2 into etc. into qt. 1 can be rewrite as in this way. Means this n by p1. What is n by p1? Here n by p1 equals p2 into etc. into ps equals q2 into etc. into qt. Means you can divide throughout by this p1. Okay. So n by p1 equals p2 etc. ps equals q2 etc. qt. Now if s greater than 1 or t greater than 1, if s greater than 1 or t greater than 1, surely this 1 less than n by p1 strictly less than n. Okay, 1 less than n by p1 less than n. Now, but what is our assumption? We can assume or we assume that the result is true for every integer greater than 1 and less than n. So, according to that argument, the result is true for this one. Means this result called for this result is called here. That means here s equals t. Therefore, the uniqueness is also preserved. Okay. So this is the proof of fundamental theorem of arithmetic. First, we assume if there is the possibility n can be expressed as a product of primes p1 etc. ps. If possible, it is q1 etc. qt. Now, for the uniqueness, we have to show that s equals t. So, since then p1, p2 etc. ps equals q1 etc. qt, means this q1 etc. qt can be expressed as the multiple of p1. That means p1 must divide this q1 etc. qt. P1 divides this product q1 etc. qt means P1 divides qi for some I, at least one of this qi. Okay, but in particular P1 divides q1. This is possible only when P1 equals q1. Why? Because P1 and q1 are primes. Then you can replace this q1 by P1 in equation 1. So it can be expressed as n equals P1 P2 etc. ps equals P1 q2 etc. qt. So by n by p1 equals p2 ps, that is q2 qt. But for any s greater than 1 and t greater than 1, surely this 1 less than n by p1 less than n. Okay, but here we assume that the result is true for every integer greater than 1 and less than n. Therefore the result must hold here. That means here this n by graph has two factorization of this n by p1. That is p1, p2 etc. ps. That is q2 etc. qt. This is the factorization of this n by p1. So these two factorization, by induction hypothesis, the factorization of this n by p1 are identical. Why? Because it is true for every integer n, every integer less than n. Thus, the factorization of n by p1 or these two factorization of this n by p1 are surely identical apart from the order of their factors. That means s equals t. Hence, the uniqueness is preserved there. Okay, so this is the fundamental theorem of arithmetic. Clear? Right. Now, in factorization of integer n, if the distinct prime factors n are p1 etc. pr, and if pi occurs as a factor of times, then this n equals, if this product, then p1 power a1 into p2 power a2 into etc. into pr power ar. That means n equals product I ranges from 1 to r. It is pi power ai. So every composite number can be expressed as the product of primes, or it is if the primes are repeated, then it is can be expressed as n equals product I ranges from 1 to r pi power a. Okay, thank you.